Hello, good afternoon. Welcome to the class ECE341, the probability and stochastic process course. We just finished the midterm exam, and now we will start a new step, new materials. So far, all the calculation we used. When you want to find some result, you just need some multiplication, you do summation, some basic algebra, right? Some basic algebra. And start from now, we will go to another step, another stage. We need to use integrals. Integral, derivative, those tools coming from calculus. So kind of a modern math, right? Let's go to ECE341. This is which week? 6th week for Friday, right? Friday. So we have studied the random variable, right? Random variable x. It will have some random value, and each one with a kind of probability, right? We use random variable to describe a random experiment. We give a number for all the result, right? Actually, we have studied an example, right? I start from that example again. We consider tomorrow's highest temperature, right? Temperature T. That will be a random value. So far we don't know what it is. Then tomorrow in the afternoon, you should know which will be that number. But so far you don't know. But we can have an average estimate. It should be some value. I think it's between 70 to 80, something like that. So we can think T, a value between 70 or maybe lower, 70. I think the highest temperature, right? Between 70 and highest, can it over 80? Less chance, that's 85, alright? So like this. You have the value between 70 and 85. But which one, you don't know. So you have a continuous interval. This is the interval, 70, 85, and interval. Alright, an interval. It is not some single values, a list of single values. You have all these values continuously, from 70 to 85. All the values between 70 and 85. For this kind of things, if you consider the probability T equal to 80. What it is? Can you give an answer? Okay, you will see this is 1 out of how many possible? Infinite possible. That will be 0. Make sense? It's 0. Okay, then you think, okay, then for x outside this interval, it still be 0. What's the difference? It's 0, probably 0. Okay, so this is the case. You cannot consider a single value, consider probability of a single value, but you can consider probability of an interval. You can consider interval. You consider small interval inside these. You consider this kind of sample space. You can consider interval of this sample space. Then you can have the probability of that interval. So in this case, we can have a probability, the temperature between 75 to 80. Right? We can consider this probability from 75 to 80. We can consider probability here. Now what is the probability? You can think like this, right? here's 5, right? 75 to 70 to 75. Then 75 to 8, another 5 degree. And 80 to 85 is another 5 degree. Okay, you can think this is 1/3, or like 5 over 15, right? You can think like that. The probability. Right? You can have an interval. This interval. Then you can use the length of the interval out of the length. Both are lengths. The 5 length of 75 to 80 is 5, and the length of 70 to 85 equal to 15. Then we have the probability is 5 out of 15. Does this make sense? This makes sense, right? You cannot consider one point, but you can consider an interval. In this case, you can compare the length of the interval. Then the probability will be the length of that event out of the whole event space with the length 15. Then you can have a probability. So we can have these. We can have this kind of probabilities. All right. And in this case, remember before the midterm exam, we have the two functions for a random variable. We have PMF, probability mass function, and the probability cumulative probability distribution function, CDF. We have these two functions, right? I said T, right? This is probability mass function for that T at a temperature T. What it is? I would say it is always 0. It's always 0. So it's meaningless, no use. Useless. It's always 0, nothing, right? You cannot get necessary information about it. But we still have these. We still can have these. This one, now we use the length from, now is totally is 70 to 85. And this one, actually this is a probability, of capital T smaller than or equal to lowercase t. So suppose this is a T, then is this side, right? So this is the length will be T minus 70 out of 85 minus 7. This is 15. The overall is 15, and the numerator will be T minus 7, right? So we can have we still have this one. Of course, we need a requirement T will be value between 70 to 85, right? 70 to 85. If you consider all the T's, if T larger than 85, then this one, it must be 1, right? Always happen. And if T smaller than 70, I would say impossible. It is impossible. Tomorrow's temperature, the highest temperature will be lower than 70. I think so. Very similar with today, right? I don't know what is today. I'm imagining today is a Friday of the 6th week. But actually, I'm recording this one in different day. So but I think that will be fine. I just imagine. Okay, suppose this one is 0. Okay, so we can have CDF for these random variable, capital T. If the value T, lowercase t, is value between 70 to 85, then we use this formula to find CDF. Oh no, CDF. Sorry, they should be use FT. The PT is a mass function. The FT is a CDF. This is a PMF. This is a CDF. Yeah, this is F, capital F. So we know this formula for T between this interval. between these two values. And when t outside this interval, then we have either it is 1 or 0, depending t is large or small. Right? And now we can have a graph to see how it looks like. Ft. Okay, I suppose here's the 70. Alright, here's 85. Then before 70, when t is smaller than 70, it is 0. And when t is larger than 85, it is 1. Here's 1. Right. And between 70 and 85, I have this one. So it is this is straight line, right? It's a linear. You have a t. The order of t is 1. So this is a linear. This gives you a line, give you your straight line. The straight line, the slope is 1/15, 1 of 15, right? 1 over 15. So the slope is a positive slope. It is a straight line, grow up gradually, right? Like this. This is, if this is 15, this will be 1. Things like that. The slope is 1 over 15, right? Slope like this. And what is this point? The ramp start at this point. What is this point? You check when it is 0. When t is 70, it is just 0. So this point is just according to t equal to 70. So here, it starts from here, a ramp. And when t go to 85, minus 70, it is 1. It is 15 over 15, it is 1. So this point is just at 85. T is 85, right? T is 85 minus 70, you get 15. It is 1. Okay, so 70 is 0, 85 is 1. So this is straight line. Looks like this. Alright, now we have the CDF, right? We have CDF. So this is a, we compare this with previous, we already studied some random variables, right? This is different. For the early examples, we know they will be a kind of sequence of values, right? We compare with the model of the dice model, right? Then we have x could be values 1, 2, 3, 4, 5, 6, and the probability will be 1/6. All of them are 1/6. So we have mass function PMF. Its value will be 1, 2, 3, 4, 5, 6, and each with probability, same probability, 1/6. 1/6. And the CDF, it will be like this, stairs. One here will be 1, 2, 3, 4, 5, 6. So this is 1/6, 2/6, 3/6, 4/6, 5/6, 6/6 is 1. Right? They look like this. We compare these two. No PMF. For our example here. No PMF. But we have CDF. It is like a ramp coming up. And the dice model, we have both PMF and CDF. The CDF is still kind of things a ramp, but this ramp is people make stairs here. People make stairs here, so it is not a natural ramp. This is a natural one, right? It's a ramp. It's like you climb on the mountain. But here the mountain people make a stair here. All right. then we have name for these two kind of random variable. This one we call it continuous type random variable, and this one it is a discrete type. Random variable. And yeah, it makes sense, right? When you see if the random value can only have some discrete values, so this is discrete type. And when the value can be continuously located in some interval or even on the whole real axis continuously, then in this case you check the CDF. The CDF will be a smooth curve. Yeah, it is smooth, right? Smooth, no jump. This one you have jump up. This is discrete type case, and here is smoothly. And of course, if you can consider the PMF, it always to be zero, nothing, right? Yeah, you can think no. You are thinking you have that, but it's zero. It's meaningless, right? You don't use it. Okay. So this is a kind of definition of the continuous type random variable and the discrete type random variable. I didn't state the definition here. Do we need that? Yeah, it's hard to say, but the meaning is quite simple, right? The value only some single values, or maybe you have infinite single values, but each values they are separated. They are not continuously. Then it is discrete type, and the value is continuously in some interval. If you just check one point, the probability that will be zero because it's too many continuously result, right? Interval, all the value in the interval is impossible. So if you check just one point, the probability definitely should be zero, but you can consider the intervals. Actually here the value in the CDF, every value here is a probability of the interval from here to all the left side, right? So this one gives the probability from 70 to this point, right? Things like that. So you can have the interval. Every interval you have a probability. So this is a continuous type. And this here I just give you example. This is just one example. Where is this one? This is just example. I suppose the probability is a kind of uniformly proportion with the length of the interval. But this might be different, for different model. This rule may have, may not have, depend. Not always looks like this, right? But this is just example. The feature for continuously random variable is just like that. Yeah, it continuously. If you check CDF, it will be a continuously curve, a smooth curve. And for discrete type, this will be CDF will be a steer-like function, and all the steers. You check the steers. You put the value of all the steers. You put it here. You get PMF. Okay. This one actually you can do similar thing. You think they are steers. Then every steer you jump, it's just kind of zero, right? This steers is the distance in each steer is just zero. So you check this one, no, it's just zero, no value, always zero. Okay. All right. Now we know what is a continuous type random variable. Right. But then the problem is, can we have something similar with PMF? Okay, we have that. We call the density function. Remember, in physics, you should have these concepts, right? When you calculate the mass of an object, you can think of the density. Like you have a bar, like you have a bar, right? So this is a bar. Then each piece, each point, the density might be different, right? Look like this one. Here you have a metal here, so the density should be higher. And this side, no metal, totally plastic, so the density should be lower. When you want to calculate the whole mass of it, you can work as an integral all the density together. You can have the mass. Now we have similar thing. We have density function, probability, density, DNS, I think. Density function of continuous type random variable. I say that is x. It's a lowercase f, capital X of x. Its definition is I use a limit. I use dirt tend to be 0. Then the probability. Here's x. We check the x, capital X, the probability of capital X between x to x plus dirt over the probability. Oh no, here's not over. This is over dirt. Like this. So we can define this is density, right? You think like the value between here between 70 to 85. Then you check a small interval from x to x plus dirt. Then you can have the probability of this part, this small piece. You can have the probability. Then this probability divided by the length of this interval. That is the density. And of course I want dirt tend to be 0. Yeah, the limit. Okay. Do you know what it is? What is this? Is this familiar? Okay, this is just I write it this way. Limit dirt tend to be 0. Denominator is dirt. Numerator now is the probability of this interval. So we can calculate this by the CDF. By CDF, it is a f x at x plus dirt minus f x x. Make sense? This one is the probability x is smaller than or equal to x plus dirt. And this one is the probability of capital X smaller than x. Then you do subtract. There will be the probability for x between lowercase x and x plus dirt. Right. The only thing might be a little bit confused is here equal or not equal. For discrete type, the equal or do not equal, that makes things different. But for continuous case, now we consider continuous type. This single point, its probability is just 0. So you have equal here or you do not have equal here, doesn't matter. For continuous type, doesn't matter. So I just put equal here. Alright. Okay. So we have this one. And what is this? This is a derivative of f of x. That's it. So we can have a density function. This one is a kind of definition. So what is density, right? The probability of that interval divided by the length of the interval. We call this the density, right? Makes sense. It's density. Then we know, okay, so this is just the derivative of the CDF. Okay, after we have these, then we can find the PDF. We call this is a PDF. Right? Probability density function, the PDF. So we can go back to the first example. We can have PDF of that one. So let's say the example. continuously. We have t, right? We have t. We have CDF of t, that is ft of t equal to it will be t minus something. That's here. It's here, right? We have this one, and this one. So we start from the left to the right. So it is 0 if t smaller than 70. And between 70 to 85 is this one. It is t minus 70 over 85 minus 70 if t is a value between 70 and 85. Now you can put the equal here. And then it is 1 if t is larger than 85. Alright, so we have these three cases. Alright, then the PDF density function t is ft of t, which is, you take derivative, then 0 is a constant, right? Take derivative, you get 0 again. So in this case t is 0. And this part, this is a, okay, we can do a simplify. This is 15, right? 85 minus 70 is 15. So it's 15. T minus 70 over 15. Oh, I did it. It's here. Yeah, I forgot this. I already have this one. Yeah. So you take derivative, you get 1 over 15. In this case, if t is between 70 to 85. And 1, when t is larger than 85 is 1. You take derivative, you get what? 0, right? It's constant. This is 0 if t is larger than 85. Okay, then we can see it in the graph way. From 70 to 85 it is 115, and these two sides, this should be 0, so it will look like this. And this one is, it looks like this, right? This is a f, this capital FT. This is T. This is T. This is a PDF, lowercase f, T of T. Alright. This one and this one. Okay, so we can compare with that discrete type case example again. This is dice 1, right? I compare that example with dice 1. Then the CDF and the PDF, can I put them together? Yeah, you can see both, right? The discrete type 1 looks like this, and the CDF is this one. The continuous type CDF, same style, right? Compare these two, same style. Just this is a continuous, this is steer-like. And PMF and this PDF, they're also similar. You see, they're similar. Okay, so for continuous type random variable, we do not have PMF, but we have PDF. We have PDF. Yeah, we have PDF. So we can use PDF to replace that that PMF. Replace that PMF. And they are similar. All right. Then we can calculate the probability based on the PDF. To find the probability of an event like a t between 70 to 80, 70 to 80, 75 to 80. We calculated this before, right? I just use the length of the interval out of the whole length 15. Right? We can work like this. We can work like this. As follows. Probability of 75 smaller than t, smaller than 80, will be the integration from 75 to 80. The density function now is a density function. Then dt. We can work like this. We use the integral. Do you remember how to calculate this? Okay, we need to plug in firstly, right? From 75 to 80, that is 1 over 15, right? The value is 1 over 15 when t in this interval, inside this interval, right? From 75 to 80. So dt. Then we have this is 115. I move out. So this is 1 take integral. That is just t, right? It is a t, and t run from 75 to 80. So this is to 80. So this is 1 over 15. Here is 80 minus 75, which is 5 over 15. I get 1/3. We have same result. But now we use integral to calculate. All right. Let me consider example. Suppose a random variable x is continuous type with PDF f(x) of x equal to I suppose this is a absolute value, some k times absolute value of x for x plus and let me see, not absolute value, I use 1 minus is a k times 2 minus absolute value of x for x between for x between -1 to 1 and 0 for other x. Alright, so it looks like this. When x between -1 to 1, it is a k times 2 minus absolute value of x. So this should be things look like this. When x is 1, it is k. When x is 0, it is 2k. Right? Here's 2k. Here's a k. And when x is outside this interval, it is 0. So we have PDF like this. Then we can consider first one, what is a CDF? What is CDF? And secondly, we can calculate some probability, like we want to find the probability of x smaller than 0.2. What is this probability? And we can also try to find the probability of like x larger than 1, or larger than 0.5. So we want to find these two probability. Find CDF and these two probability. Okay, so we can do like this. CDF. We know PDF. We know PDF is in. We have this right. Because PDF is the derivative of CDF. So we will go back, right? Now we know this. We want to find the back. What is the capital F? So CDF, the capital F, will be integral of fx of x dx. It's just like this. Actually, this is the probability, right? As I explained here. When you want to find the probability of an interval, you just integral this density function on the interval. Now, this is the probability from where? From negative infinity to x, right? Smaller than x. This is the probability of capital X smaller than x. So this is just from negative infinity to x. All right. So we have this. We always have this. So you can find the fx by calculate this part. Calculate this part. All right. Then what it is? We can have a look. We have this one, right? We have this one. This is the formula is here. Graph looks like this, and this integral from negative infinity to some x. So when x in the negative smaller than negative 1 part, it is 0. Only when the value after x larger than negative 1, you can have integral. So here we have several ways. Fx of x, we have three cases, right? So we have this one. It is 0 if x smaller than negative 1. Yeah, equal, doesn't matter. It will be an integral. Oh, this I use this one. Yeah, integral from actually just from negative 1 to that x. It is k times 2 minus absolute value of x dx. If x is a value between negative 1 and 1, and outside that must be 1. If x larger than 1, equal, you can put anywhere if you want, you can put equal, doesn't matter. Okay, so we have this, right? We have this. Then we need to do calculation. Okay, here actually we have problem. What is this k? You don't know what is this k, right? But after you calculate it, you should know what is that k. What is this one? Negative 1 to x, k times 2 minus, okay, you know this k, this x and this x are different. I use a y for it. All right. This is variable used for the integral, and this is the upside of the interval, right? From negative 1 to that x. So this is y, and this one actually I need to calculate from negative 1 to x, k 2 minus negative absolute value y should be negative y dy if x is negative, okay. And it will be negative 1 to 0 plus 0 to x if x is positive, right? I separate because the formula in the positive side and negative side is different. For negative x here, or negative y here will be negative y, right? Absolute value. For positive y or x here, then it should be positive. So I separate like this. Okay. This part, the first part, that is a k times 2 integral, right? Integral. So it is k times 2 integral 1 integral. You get just the x, right? X, y. I use y. Y run from negative 1 to x, and then plus ky. So plus ky, y integral, you get y squared over 2, right? And y also run from negative 1 to x. Okay, this is for x less than 0. And when x is larger than 0, integral here, okay, should be same thing. same thing, just the up and the down different. So this is a k times 2y, now is from -1 to 0, plus k times y squared over 2 from -1 to 0. This is the first part. This is the first part, right? This is the integral from -1 to 0. And from 0 to x, similar with these, but here should be plus, not minus here. So I can write it directly here. It will be negative, right? Because here's a the first one is positive here. K times 2 times y from 0 to x. This part is good. But this part, because here is a plus, then here is a minus. So this will be minus. Minus k times y squared over 2. And this is from 0 to x. Okay, so this one is x larger than 0. Now both in this case. Okay, then we can have the final answer. It will be, we plug in k2, the 2k. Here's x minus -1, right? Should be x plus 1. And plus k over 2. And y squared now is s squared minus -1 squared. Right? This is the case. If x is smaller than 0. And this one, similar with that, I can just plug in, that will be fine. So this is a 0 minus 1, right? When y is 0, this is 0. It's 0. And the minus, when y is -1, so this is plus 2k. Right? And plus this one, k over 2 is same. And y squared will be 0 squared minus -1 squared. Right? So this is this term. Then this part. First term, this term is a k2y, so I write here, plus 2ky, right? And y run from x to 0, x minus 0, still x. And minus k over 2, the y squared will be x squared minus 0 squared. Okay, that's it. This is if k is larger than 0, x is larger than 0. Then we do some simplifying. I have k, I put in the front, and half of x squared, right? And we have more x squared term? No, just one x squared term. The x term is 2kx. K I move in the front, so this is 2x. Alright, I have 2x. Okay, this one used. Then constant term. Constant term, here's 2. And here's 1/2, right? 1/2 minus times -1. So 2 minus 1/2. 2 minus 1/2 is 4 of half minus 1/2, just 3 of half, right? So it's 2 minus half, right? 2 minus 0.5, yeah. Okay, so it is this one, if x is smaller than 0. And if x is larger than 0, so we have these 4 terms. All of them you have a k, right? So I still have k. And here's a 2 minus half, right? 2 plus a -1/2. So 2, this is 3 over 2 actually. 3 over 2. Okay, yeah, just k times 3 over 2. And plus, I don't need, I move k outside. Here's a 2x plus 2x minus half of x squared. Yeah, you get this. we get this. All right. Now we can have a graph. Oh no, in the middle. This is 0. This is a x equal to 0. This is x. Suppose this is -1. Here's a 1. This side is 0, and this side is a 1. And between them, here's a square, x square. So it will be, the curve looks like this, right? Curve looks like this. And this one is a curve where it looks like it's a negative, so it looks like this. But we need to put the value in. When x is 0, this is a 2/3 k, 3k over 2, right? X is 0. And when x is 1, I have 2/3 of k plus, okay, x equal to 1, that is a k times 3 over 2 plus 2 minus 1, 2. So it is k times, this is also 3/3, right? So 3 of half. This is also 3 of half. So this is totally 6 of half. So it's 3k. So this is 3k. And we know this is a continuous case. So this point, this will be connected. So we can know 3k equal to 1. K is 1/3 actually. So this point, it is just the 1/2. And how the curve connected, I don't know. It seems like square. This one should be this part. Should be like this part. And this one should be going down. Now it's going down. Should be like this. Should be like this. This part. Why is this part? Why in this part? Why in this part? Should be like this. All right. So this is CDF. F x of x looks like this. Yeah, here you need to calculate because it continuously, right? Continuously. Yeah. So this point is 3k must equal to 1. All right. Okay. That's all for today. I introduced the concept of continuous type random variable, and in this case, we know how to calculate, how to find what is the CDF, and also we introduced the new concept PDF, the probability density function of continuous random variable, continuous type random variable. It will be the derivative of this CDF, and we can calculate it based on two sides. The CDF, we do derivative, we have PDF, and then we go back with the integral. We go back, we can have fx. If I write it in this way, negative infinity to x. Here's a okay, let me write again. Negative infinity to x. This is a f capital X of, I use a tau for the, or y, the tau, okay, like this. Alright, yeah. So this seems like you have a pair, right? Similar with in the calculus, you have a function, it's a derivative, and the integral, you can go back, right? Similar. Now it's a CDF and a PDF. Okay. Then see you next time. Oh, that should be next week, right? Today is Friday. So have a good weekend. Bye bye.